Good afternoon, everyone. Welcome to our KCGC TV viewers. Myself, Dr. Shally Bhatia from Physics Department, Khalsa College, Amritsar. Today, I am going to deliver a lecture on light. So, what is light? Light is a sensation to our sight. There are two objects which produce light. First is called as the luminous object, which produce their own light, and second one called as the non-luminous, which do not produce their light, such that chair, desk, etc. And in luminous objects there are sun, bulb, they are producing their own light. So we will discuss the properties of light. The first property of light is light can travel as a beam of rays. So, and the second property of light, it is called as the dual nature of light. So we will discuss about the dual nature of light. The dual nature means the light can behave as a particle or as a wave. Light has both properties. It can show as a wave nature as well as the particle nature. So we have some phenomena regarding this. The wave nature of light is demonstrated by the phenomena called as interference and diffraction, and the particle nature is demonstrated by the different phenomena like photoelectric effect, Compton effect, pair production. So it is some experiment which prove the light can behave as a particle nature, and some experiment prove the light can behave as a wave. So light travel in a straight line. So first we discuss about the basic understanding phenomena, that is the law of reflection. So what is a reflection? When light is incident upon a polished surface, it will get reflected back into the same medium. So bouncing back of a light along the same medium, it is called as reflection. So reflection is based upon the two law. The first law is of reflection is the incident angle is equals to angle of reflection, and the incident ray, normal, and the reflected ray all lie in the same plane. So this is the law of reflection. And the second one, the angle between incident ray and the normal, it is called as the angle of incidence, and the angle between normal and the reflected ray, it is called as the angle of reflection. Now we further discuss about the next phenomena, that is the refraction of light. So what is refraction of light? It is when light goes from one medium to another medium, or light when travel from a rarer medium to denser medium. The rarer medium is that which has low density or low refractive index, and the denser medium is that which has high refractive index and it contains more density. When light travel from rarer to denser medium, it will travel towards normal. Rarer medium is like air, and the denser medium which may be glass or water. So whenever light travel from rarer to denser medium, it bend towards normal. And the second case, when light travel from denser to rarer medium, it bend away from normal. So these are the two law of refraction which we have to discuss. These law of refraction proves the Snell's law of refraction. So what is the Snell's law of refraction? Snell's law of refraction says that the refractive index of light is equals to the sine of angle of incidence divided by sine of angle of refraction. So sine of angle of incidence and the sine of angle of refraction, the incidence angle which the incident ray of light makes with the normal, and the refractive angle which the refracted ray of light makes with the normal. So this is the definition of refractive index. Now what is the absolute refractive index? It is defined as the ratio of sine of critical angle divided by sine of v, that is the velocity of light in air to the velocity of light in medium. So this is the definition of absolute refractive index. Now we move towards the total internal reflection. When we increase the angle of incidence towards more and more value, then its stage comes when incidence becomes equal to critical angle, and that case the angle of refraction becomes 90 degree. And when we increase the angle of incidence beyond critical angle, then the light is reflected back into the same medium from which it travels. So this proves a very important phenomena of light, that is called as the total internal reflection. That means the light is totally internally reflected back into the same medium from which it is traveling. For example, if a light is traveling from water to air and someone coin is placed in the tub which is full of water, and light we are viewing from the outer side, so light of ray traveling from denser to rarer medium, in that case it will prove the phenomena of total internal reflection. So there are some few examples which proves the law of total internal reflection. First one, we see the case of twinkling of stars. So twinkling of star is based upon the phenomena of total internal reflection. When we see at the sky, we see the skies are twinkling, so it is due to the total internal reflection, because when the light is traveling from the star is a point source, so the light is traveling from rarer to denser medium, in that case it will bend towards normal. So when the light reach us, it will shows that the star has shifted their position, because it is the apparent position. We are seeing the apparent position of stars, so we see that the stars are shifted at their positions, and the light of path is not straight, it is somewhat curved. So we are seeing the due to the curved path, we see that stars are twinkling in nature, so the twinkling of stars is due to the total internal reflection. And also the another example of total internal reflection is during sunset and sunrise. We see the sunset and sunrise, we are looking for it is based upon the phenomena of total internal reflection, because sun is below horizon during the sunset or sunrise, but it appears us that is it is above, lies above the horizon, that is due to the real position changes to the apparent position. It is because of the total internal reflection. So there are the some phenomena which prove the nature of light. So now we are moving towards the wave nature of light. So what is the wave nature of light? So light is traveling like a wave. It is having crust, it is having trough. So when crust fall upon crust, then it will produce a maxima, and when crust fall upon trough, it will produce the minima. So crust will increase the amplitude of the resultant wave, and the crust trough combination will lead to the minimum displacement of the wave, so it will affect the resultant magnitude. So it is a most important phenomena that is called as the interference prove the wave nature of light. It is basically the superposition of two light waves which produce the resultant wave. Now it proves the wave nature of light, and we will get the alternate bright and dark fringes on the screen. And the second phenomena that is called the bending of light from the corners of a aperture, that is called as diffraction. So in diffraction we are also getting the alternate bright and dark fringes, and we obtain a central maxima at the center and the two minima on the either side of central maxima. So diffraction is the bending of light from the corner of an obstacle. This is also proved the wave nature of light. So now we discuss the particle nature of light. The particle nature of light is proved by the most important effect, that is called as the photoelectric effect. So photoelectric effect is defined as the ejection of electron from any metal surface when a light of suitable radiation fall upon that surface. So electron get ejected out. So electron ejected because of the light radiation, so that phenomenon is called as the photoelectric effect. So this proves the particle nature of light, because the light wave consists of energy packets in the form of photons, and which are traveling with the velocity of light, that is 3 into 10 raised to power 8 meter per second. Now another experiment that proves the particle nature of light, that is called as the pair production. So what is pair production? When an X-ray photon fall upon a surface, that it will produce either particle or an antiparticle. So particle and antiparticle pair is called as the pair production. So gamma ray photon produce and one electron and one positron. So positron is the antiparticle of electron. So we will get the electron and positron pair. So this process is called as the pair production. And in the reverse direction, when positron and electron will combine with each other, they will produce the two gamma ray photon. So this process in the reverse direction is called as annihilation. Annihilation means the combination of particle and an antiparticle. So electron and positron combined will produce the two gamma ray photons. So this is this pair production and annihilation also prove the particle nature of light. Now we move towards the third particle nature, that is explained by the Compton effect. So it is a scientist named Compton that he will get the Nobel Prize for this experiment in proving the particle nature of light. In this experiment he performed when an X-ray photon fall upon a carbon target nuclei, it will strike with the electrons of carbon target nuclei. When it will strike with the electron, it will produce one scattered photon and one recoil electron. The scattered photon is scattered at an angle theta, and the recoil electron is scattered at an angle that is called as the recoiling angle, and it is indicated by phi. So theta is the angle of scattering and phi is the recoiling angle. So we will get the recoiling electron and a scattered photon. So Compton effect proves that the scattered photon is having more wavelength as comparative to incident one. So there is a change in wavelength when a X-ray photon strike with the electron at the carbon target nuclei. So that's why there is a change in wavelength. So Compton effect proves the change in wavelength of the incident and the scattered photon. So it is given by delta lambda. Delta lambda is equals to lambda dash minus lambda, that is called as the Compton shift. So Compton shift by calculation by applying the law of conservation of linear momentum, angular momentum and energy, we will got the result that delta lambda should be equals to h upon m naught c 1 minus cos phi, where phi is the angle of scattering. So we will prove it with the help of some examples. For example, when theta is equals to 0 degree, then cos 0 is 1, then in that case delta lambda should be 0. It means that there is no Compton shift. The wavelength of incident photon should be equals to wavelength of scattered photon. Now we will discuss the second case in which theta is equals to 90 degree, then theta 90 cos 90 is 0, then in that case the delta lambda should be h upon m naught c, and when we increase the theta to be 180 degree, in that case delta lambda comes out to be double of 2h upon m naught c. So we will see that with the increase in angle of scattering, the Compton shift goes on increasing. So this proves that the angle of scattering goes on increasing and the delta Compton shift will goes on increasing. So these all experiments prove the particle nature of light. So that we have discussed in our lecture. So we have discussed about the various laws, various properties and the dual nature of light by proving some experiments. So this is about our lecture. So thank you.